Okay, so this is our group project one, and I'm Peyton.
I'm Ethan.
I'm Seth.
So this is our problem description. You have designed a helicopter for the next Mars rover. The helicopter is designed to launch from rest at little t equals negative capital T, after which the helicopter flies for some time before landing a known horizontal distance d away. Capital T is an unknown but constant time. During this motion, the helicopter has the following acceleration as a function of time, where alpha and beta are known constants. And then we're given the acceleration formula. And then we're asked to describe the motion of the helicopter. How much time does the helicopter spend in the air? And where does the helicopter land? This is a video of NASA's Mars rover, just for context. So the first thing we want to do when approaching a real life context problem is identify important quantities and variables. So our known quantities are constants alpha and beta, our final distance, or in the x direction, and our acceleration is a function of time represented by the function given in the problem description. And then our unknown quantities is the initial time, which is capital T. And important formulas we identified were distance, which is the square root of x squared plus y squared. Velocity is the integral of acceleration, and position is the integral of velocity. The second thing we want to do when approaching a real life context problem is identify the assumptions that we are making. And the assumptions that we made before approaching this problem were that the helicopter is at rest when lowercase t equals negative capital T. The problem occurs in 2 dimensions. When delta x is equal to distance, the helicopter stops moving, and the helicopter accelerates in the positive x direction. And then known constants alpha and beta are greater than 0.
So from the problem, we were given a solution in which we took both the velocity and the position vectors. And from what it looks like, we converted them into both general net change in position, while also figuring out a general net change in time. And this could be modeled with the 2 bottom equations here, with delta RT, which is equal to dx plus alpha d divided by 35 beta. And then delta t, which is equal to 2 big T equals 2 square root of 3d2b. These would become beneficial in figuring out the final position and how the helicopter's motion behave during the equation. Then from those, we figured out a couple of graphs that helped model both the acceleration, the velocity, the position, and also just the general motion of the helicopter. So in the top left corner, we see an acceleration versus time graph. We see how the acceleration generally decreases and goes down in a linear fashion. In the middle, we see the velocity versus time graph, and we see that there's a gradual decrease. It's not as steep of a decline as compared to the position decrease, but as you can see, there is one. And then in the top right corner, there's position versus time graph. We see it has a sharper decrease, a bigger decline than the velocity graph. And on the bottom, this shows the general motion of the helicopter. You can see how it goes out to the right into the positive X quadrant, and then circles back and goes left into the negative quadrant. And then an important fact is that we need to define and make sure that the dimensions were proper and that no units were incorrect. So we went through the process of figuring out what these different variables equated to and making sure that they all equated to meters per second squared. And we've successfully confirmed that with this first equation here. And then we also had to make sure that time was in seconds. So cross-referencing the different variables, we figured out that they were indeed in seconds.
All right, and last up, we have sense making. It is very important to examine the relationship between the different constants and how each of them relate to each other physically. So we have beta, which is used for the x dimension, and alpha, which is the constant used for the y dimension. So changing those independently wouldn't necessarily affect the other, but it would affect the big T constant. And also the constant d is used in both dimensions for determining the total distance that was traveled. So since they're all known, we know that they all relate to each other in some way. We also know that both beta and d are used in the equation of big T, as given from the previous solutions. But d is in the numerator while beta is in the denominator. This means that an increase in d or a decrease in beta would result in an increase in T and vice versa. Lastly, for our conclusion and comparison, we know that this helicopter real-world context problem can be compared to a couple of practice problems we have completed during this course. These examples help us work on and develop an understanding of efficiently completing multi-step and multivariable problems. So one example we thought of was the dragon boat problem from in class, as well as the bike and stoplights homework example. So some similarities were that they used integrals and had an unknown time constant value that we had to solve for. But some of the differences were that they were much simpler, as acceleration, like the equation for acceleration was much simpler, and they were only in one dimension. Another similar problem was the throwing a ball at a cliff from homework 3. So another similarity for that problem was that we worked with different x and y functions, and a difference was a more standard projectile motion problem rather than these more dynamic acceleration problems. All right, and that concludes our project. So thank you all for listening.
Thank you.